Thank you very much, and welcome to yet another episode of Tech for Impact. I'm your host, Siro. Today we have a special guest. He is the chair for the SPE Research and Development Technical Section and the Wealth Ambassador 3 for the race group. We have the one and only Mr. Jeff Bailey with us. Today's conversation will go through careers, PHA design, ruling vibration, to name but a few. Or like Mr. Jeff likes to call it, co-featured series with Jeff Bailey and Siro. So stay tuned. Welcome, Jeffrey.
Thank you for having me.
Could you take us through your career and your journey as a person?
Okay, well, thank you for the invitation. I'd like to do that. So I'm calling this a coffee chat about careers in oil and gas, and because I've worked mostly in the drilling and subsurface area, my examples will be about that, but hopefully there's, some lessons that generalize to other fields as well. And our basic agenda, which Mercy, you so well laid out before we did this, is to start with a sort of a brief discussion of my career journey and my experience in drilling engineering. And I do have a specific expertise in drilling vibrations. So we'll talk about that a little bit and the importance of effective BHA design and why I think we're, as a rule, not doing it, as well as we could today in many cases. Talk a little bit about how data and engineering decisions contribute to safer, more efficient drilling. I've got some experience with that. And I have somewhat less experience with autonomous downhole systems, but make a few comments about this, the opportunities and the challenges they present, and talk about the future of intelligent drilling technologies. And then finally wrap up with discussion of, advice for students and young professionals who are interested in pursuing careers in drilling and oil and gas or energy engineering, if you want to extrapolate to geothermal and maybe some other areas. So sound like a good way to go?
Yeah, let's get to it.
Okay, thank you. So my dad was actually a mechanical engineer, and there were various activities we did when I was growing up that involved science, technology, and engineering. So I guess I had an early interest in that when I was very young. When I went to college, I really liked courses in math and dynamics and fluid mechanics. And I guess because of my interest in those areas, math and dynamics in particular, I kind of went down the physics track, and I really liked electromagnetism and optics. I had a really interesting class in optics, which actually I used some of the methods in my vibration modeling that I learned in my optics class. The professor was actually a Nobel Prize winner. But when we got into some of the other areas of physics, I got somewhat less interested, and I started taking classes more in mechanical engineering. I did the entire thermal sciences course series in fluid mechanics at Stanford, while getting also the physics and also an economics degree. So I took 5 years in college, which, like in hindsight, was probably too long. But along the way, I did take a class in energy and society with a professor who I did a lot of work for later. But I was really fascinated by these spaghetti diagrams of energy flows of like oil and gas, but also electricity, all the different ways that energy pulses through our economy, a global economy. And as it says here, I was, I guess, a senior in high school during the energy shock of 1973. I was graduating in 1979 from college when we had another oil shock, and I do remember the gas lines, and they were really terrible. If you find that people don't like high prices, you'll find that they really, really don't like not having access to petroleum at any price. And really is oxygen for the economy. It's like what makes everything tick. And I think we're, maybe learning that again.
Yeah.
My first oil patch job was when I joined Shell in, I guess it was 1981. in the area of geophysical computing. They had one of the largest data centers for seismic processing. They had, I guess it was 9 spare UNIVAC mainframes, and they had these attached. There was a new box was coming on, an attached array processor, and they ran a lot of the correlations, convolutions, and things like that over on this array processor. And so my job was actually to take the Fortran code that was written in do loops and convert it to a format that could be vectorized, so it could be pushed out to the array processor. And the array processor exactly is pretty much like what a GPU is today. You know, it's a pipelined in parallel architecture, only very primitive compared to what you find in your laptop today. So, but that was a very interesting job. I learned a lot about geophysics and computations of that in that job. But, you know, I got to a point in my, I guess it was after 3.5 years, when it was like now or never point. It's like either I'm going to get my doctorate or I'm not. And so I did return to graduate school to get a doctorate. It turned out it was actually not a bad time to be stepping away from the industry, because there was a pretty big crash the year after I left in 1986. So it was a boom bust period. And then I graduated, and I did a fellowship for 1 year, and then had an opportunity to join Exxon Production Research Company in 1989. That was really when the hiring just started on the other side of the 1986 crash, so timing wasn't bad. And I was put on a drilling research project, which was to look at bit walk. This was before we had rotary steerables, way before rotary steerables, and we had bent sub motors a little bit. It was just kind of coming into the industry at that time, but there was still a lot of applications for rotary directional drilling. And what they would do is they would position the stabilizers on the BHA and specify their diameters such that they got a certain build or drop rate. So they could build angle just by changing the stabilizer configuration, essentially. And then a side effect of that was sometimes the BHAs would walk to the right or to the left. And as they did that, you know, they would go off trajectory and have a hard time actually steering it back. So what they would do is, coming off some of these platforms, say in the Gulf, they would lead the angle. Say it was going to walk to the right, well, they'd lead to the left and then watch it, you know, veer around to the right. And so they would do these calibrations, but they were really trying to solve the problem of walk. And so Exxon had this test frame out at their Friendswood test facility. My job when I started was to make it operational and then try to figure out walk. And I don't really think I figured out anything about bit walk, but I did develop a vibration model coming out of that, which years later would actually prove pretty useful. But after I worked on that project for several years, and we had 1 or 2 applications in the Gulf off of Mobile Bay, which were promising. You know, we made some predictions of changes in assemblies that seemed to actually help reduce vibrations, but they transferred me over to work on fracturing, and because of my geophysical background, they put me on a project to measure microseismic events that are generated from the fracturing process. Like when you pump a frac job, you displace the earth, and then there's leak off of fluids, and as the pore pressure changes and these fracture plates shift a little bit, they change the stress locations in the formation, and when they move, they generate these really small earthquakes or tremors, like -3 to -5 in the magnitude level. And if you have a tool down there, you can hear them and then map where they came from and then infer the fracture direction. So for the next, I guess, almost 15 years, I worked on that technology and also a bit of fracturing along the way. So it was a a diversion from drilling vibrations for sure. But back in, say, the early mid-2000s, the drilling company got interested, development company got very interested in reducing vibrations. And so the people remembered that I had done a research project before on drilling vibrations. And so we restarted a project, and that led to what I did for the next 15 years. And this is one of my favorite slides because it kind of captures the essence of the problem. You know, if you went to a music concert and the musicians did not tune their instruments, you know, what would you expect the result to be?
I think it will be chaotic because like the guitars and all, hey.
Yeah, it'd be very bad.
Yeah.
So I kind of see that that's what's happening in a lot of drilling applications today, is that vendors show up on location with equipment that is not tuned dynamically, and they don't really recognize that a lot of the positions of the stabilizers are incorrect for the conditions that they intend to operate at. And so if you compare, say, a violin on the left with a bottom hole assembly on the right, so technically the violin is pretty well represented by a second order differential equation. The bending stiffness of the string is not significant. And there are basically two nodes. On the bridge, you have one nodal point on the and then on the where you put the finger along the neck of the instrument is the second nodal point, and that length of that string and the tension and the properties of the string all determine the note that's played. So that's a fairly simple second order system. A bottom hole assembly is actually a lot more complicated. It's described by a fourth order differential equation because you really can't ignore the bending stiffness. And then you have possibly many nodes. This is actually an example of a bottom hole assembly that has 1, 2, 3, 4, 5, 6, 7 nodal points in the first 100 feet of the bottom hole assembly. And it turned out that this assembly operated very badly in the well. It wasn't really fully appreciated before the run how bad it was. But in the modeling that we do, it looks terrible. And there's an SP paper that describes this. And this and the previous slide are from a distinguished lecture that I had in 2020 to 2021, in which I go through several case studies of this, and you can find it on the SP energy stream if you look for tuning a drilling assembly like a violin. It's about, I don't know, 45 minutes or something in length. But this is much more complicated because this is a fourth order equation. You have multiple nodes. And, you think about, well, how can I rearrange this assembly to reduce the dynamic problems? And so what we do in that technology is, we'll, for instance, take this stabilizer out and compare the model results with and without that stabilizer nodal point, and then see, oh, are we making progress or not? Then maybe we'll, move another nodal point. And so we adjust the BHA design in order to minimize a vibration index. And it's been pretty beneficial, and it also is very important. So this is an example of the improvement that you can see over various degrees of optimization. The first, the gray line here was from a well that was an exploration well before they realized that there is about a 400-foot interval of, I guess it's a calcite cemented sandstone. So it's very hard and pretty slow drilling. And they did, let's see, 1, 2, 3, 4. I think they set pipe before he even left, and exited the formation. But they had a lot of difficulty getting through this. It took them almost 250 hours to get through it. So there was a pretty big amount of effort put into improving this operation. And in successive wells, we did many things to make it better. One of them was improving the BHA design. Another one was changing increasing the drill pipe diameter to reduce the stick slip. But there was a lot of bottom hole assembly optimization, and there's papers that discuss this in more detail. But you can see that we went from being on the order of 10 days to being on the order of 1 day to get through this formation. So that's for an offshore rig in deep water, that's a very significant amount of money and efficiency gained by just changing the dynamics of the drilling process.
Okay, so the drilling vibrations are connected directly to the BHA design. Like if you have an effective BHA design, the vibrations will be less.
Yes.
Which is more efficient.
Yeah. Mm-hmm.
Okay.
So people have a misconception about stabilizers. They think that, well, if you put a stabilizer in a location, then it's going to make the deflection zero and therefore eliminate the vibration. It turns out that there's a side effect of putting a stabilizer in a certain location. It creates a stress concentration and can cause a impediment for you want to have the energy be able to be distributed up the drill string. And what happens when you have too many stabilizers too close together is that you trap a certain amount of energy in the drill string and it cannot get released up the string. I know that's a very wishy-washy sort of description, but we have a model that actually can predict this. Like having these two nodes very close together can cause a resistance, and there's a lot of interference between nodes that can be too close together. This problem up here was an issue, and this problem down here, the run before this, they had only one roller reamer, and then they added a second roller reamer. And this run was actually the only time that many people that I'm familiar with recognize that a roller reamer failed in the hole. So it's a very rare event, but it happened on this run with this BHA because the vibrations were so bad with this design. So it is, it's significant and can lead to huge performance changes.
Yes.
So let's see, how data and engineering decisions contribute to safer, more efficient drilling. Well, well surveillance is certainly a very important aspect of drilling safely and efficiently. You always have to know what's happening in the well. And there's always been a lot of concern about data quality and making sure that sensors are calibrated, the data is flowing properly, all the systems are recording. And then I'm finding that, with all the improvements to technology, the data storage and processing is becoming more efficient daily. It used to be that you had satellite connections, and now there's just, in some places there's fiber optics to shore from offshore facilities. There's just a lot of improvements in the whole data area. And digital twins are becoming applied more widely. There's increasing appreciation for the idea of the digital twin, where a model is following what's happening in the well, and you're able to look at your engineering parameters and see how they're trending. And it's more efficient drilling is good. It reduces time of the well, and when you reduce the time of the well, certainly the cost goes down, but the risk goes down as well because you're having less time in the well, for instance. So I think there's been huge improvements in data and engineering decisions in the last, 10 or 15 years. And it seems to be increasing. And all the digital technology is helping.
Yeah, it's like I was surprised when you started and you're saying you had to convert data from Fortran so that it can be processed in the rig. It seemed like it was hectic. And yeah, the transition to now, so now it's faster. So like, yeah.
Yeah. So the evolution towards trusted autonomous downhole systems and the opportunities and challenges they present. I'm not an expert on autonomous downhole systems, but I have a few general thoughts. There is an increasing autonomy of downhole tools. I can't remember what the vendor is, but for a long time, there's been like a rotary steerable that just said, okay, I'm going to try and keep the hole vertical. And they just put it in that mode from the surface. And as they drilled ahead, the tool was constantly adjusting and had, gyro or accelerometer package that was trying to keep the well vertical. So that's like maybe first level of autonomy in a directional drilling application. But it's evolved from there with different hole angles, of course, and then you have measurements of the formation, the borehole, like diameter, the petrophysical properties and whatnot. There is a certain amount of autonomy in inflow control valves where to meter the flow at the wellbore. And there's increasing autonomy of automation of surface equipment. There have been applications of wells that have been drilled with like no people in the red zone on the rig floor, where all that is mechanized and automated. And there is an increasing trust in technology when service delivery is good and the operational problems are tolerable. And we seem to be pushing this envelope back continuously all the time. So there's increase in comfort with some amount of automation. They're doing useful things, and the problems are, becoming, less frequent and more tolerable. So I think there is an opportunity to identify and develop more autonomous tools. And of course, the challenge is to make them trustworthy and make them the first choice where they're preferred as safe or safer than the alternative, and they're working very well. So that's kind of where I see this stuff going. It's just over time, this envelope keeps pushed back more and more.
Is the industry ready to adopt the autonomous downhole systems?
Yeah, incrementally, I think so. Yeah. Again, it's application by application. Is there a tool that replaces something that is not autonomous today? Does it work as well? And is it trustworthy? Is it reliable? And does it then on a cost and performance basis become the first choice? I think that's just going to continue over the next 10 years, probably be increasing amount of improvement in this area.
Okay.
So regarding intelligent drilling technologies, that brings me back to the thought about digital twins. And I do think it's a logical application of physical models and real-time data is the intersection of those to examine deviations between data and predictions with a purpose to improve the operational performance. In control system terminology, we call this an observer. And it's a model that just basically is a digital representation of everything that's going on in the real world. But this is essentially an extension of, I think it was Jeff Moss called it a trendology, where people just look at trends and look at deviations from trends. And I guess one application of that would be, say, maybe there's a 10% error in your torque measurement at surface, for instance. So you may be looking more at the changes in the torque. You may not know that there's a 10% error, but if you look at the changes, like it's increasing faster than it should be increasing, then maybe you know that you have a problem in your hole. You think about digital systems, well, you're going to calculate what the torque should be, if your measurement's 10% off, then, maybe you've been seeing it for the whole well, and now you're making adjustments. I think we have to figure out how to close the gap between instruments that aren't giving us the values that we think, because maybe the gauge isn't perfectly calibrated. But I think we're going to be able to, over time, maybe make adaptation to that. We're probably going to have a hard time getting perfect measurements all the time, but we'll have models that think that we need perfect data. So there's a little bit of tension between those things, but perhaps we can develop technology that can take account of that, right?
Yeah.
So I see basically there are two classes of tools. A surveillance technology is one that has a time factor of maybe minutes or hours. You can start to see emerging problems, and operations personnel can be informed, and they can make decisions on what to do. And, that's something that's viable with a data center, for instance, working with a rig. So you have the rig site personnel, you have the data center personnel, and they're running a model and discussing, what's going on with the operations personnel at the rig every now and then. Then there's a case of in-the-loop technology where, the things happen almost instantaneously, and you can't have a loop like that where people are doing surveillance and discussing what's going on. And a really good example comes from this well, which is a redrill on the Statfjord platform, well C16A. I think it was in 2016. There was this long 12.25 section, and I was trying to find the SP paper on it last night, but there's an in-the-loop control system that when they're coming out of the hole, they detected a pack off, and instantaneously, went back down and started rotating and circulating instead of tripping. Because if there are a lot of wells where if you keep coming out, you're just going to plant the BHA, and then, you may end up sidetracking the well. But if it acts within seconds, literally seconds, you have to react. And, that has to be in the operational system of the rig. It has to be in the control system. So I think there's a place for both the surveillance level and in the loop control systems to work on this sort of problem. So looking at advice for students and YPs interested in work in this area, my first rule would be don't take as long to make up your mind on what you want to do that as I did. I feel like I had kind of a long and tortuous road to get to where I am, but maybe a lot of people feel that way. And then what do you need to know? I think you need to know a little bit about a lot of things, and do this by growing your awareness level. Early in your career and when you're in college, you should explore a lot of different areas. In particular in energy and oil and gas, learn about reservoir, learn about completions, learn about drilling, learn about geology, learn about maybe even geophysics. Be aware of a lot of different things in the industry so that you have a big picture view. And then over time, you may find an area that you really are more keenly interested in diving deep into, and over time develop an expertise in one or two areas that are kind of related so that you can be the go-to person for that. But in the meantime, you have kind of a big picture view, but you've got a specialty. And so for awareness level must-haves, I would say basic math, science, and engineering background is really essential for technical competence. And so try to develop that when, early in your career, say in college or, or first few years of employment. And in particular, if you're in the drilling subsurface area, understanding field and rig operations is extremely helpful. I guess it just takes an appreciation, understanding of what's going on there. Someone once referred to the rig supervisor as the mayor of a small town, and you have to kind of understand what goes on at the small town to sort of be impactful in helping them with their problems. And then I'd say that digital is pretty much a required skill for many tasks today. There's certainly a lot of technology that changes like daily, which is kind of hard. You know, of course, I did Fortran, then I did C, now I'm doing Python. And so I'm doing graphical charts, and I started using Matplotlib. And then someone said, well, you need to use Plotly. And then, you know, before I even learned Plotly, the guy saying, no, you need to use Bokeh. So, you know, I didn't have to learn Plotly because I could go just straight to Bokeh. Yeah, it's like how these things change faster than you can learn them. But, you know, I'd say this may become less burdensome as AI develops. And I just had a recent example of that where the Python libraries are migrating from one library set to another library set. And there was an error in my setup configuration because it was still looking for the old libraries. And someone suggested, well, let's use Copilot to figure out the commands to fix this, and put in a query. It came back with a set of commands that I don't know how long it'd take me to figure it out, but it worked. It actually deleted the old libraries, and now it just looks at the new libraries. So yeah, maybe AI will help us understand how to work digital more seamlessly. But you know, digital is really important, but oil and gas is not underneath your computer. You have to actually go out to the field. So that's why I go back to, you know, for some tasks, really understanding rig operations is really extremely helpful. And the last thing, you know, be ready to question things you don't understand. And don't be pressured to do things you feel are not right. Ask questions. And always remember safety is first priority. And so the bottom line here is, I think success equals skills plus a positive attitude plus ethics. And if you have all those three things, you will be successful in your career.
So I have a question. With digital transformation, because it's changing every time, how do you stay keen to that sector? Like, you know, I have to learn this and this and this. And how do I ensure that I've learned this? Mind you, it's changing every day. Like tomorrow, it may be a new thing. So how do I ensure I'm doing the right job?
I was just going to say that there are some AI tools that can translate from one language to another language now. So that may be, you know, some degree of help on that.
Yes. Okay. If you had to explain the BHA design using the earlier images, the earlier image, how would you explain it?
We've developed a model that helps us, and sometimes I can predict what the model is going to do, and sometimes I get a little bit surprised. But it has to do with, it's a mass spring system with, you know, relatively complex parts. So I would just say, I guess rules of thumb would be, if I look at this BHA design, I'd say, okay, I want the bit to be very well supported. So I will go with fairly close spacing of stabilization near the bit. But as I get away from the bit, I want to start to increase the spacing between stabilizers, but in such a way that I have a sweet spot at my rotary speed that I'm going to operate at. And sometimes, like if I pick up a basic BHA, many times I've seen this, the response is coming down that would be very, very smooth at, say, 250 or 300 RPM, but we're drilling at like 150 RPM. So I find that a lot of stabilizers are too close together. So I start to space them out, and you want to increase the spacing as you get further away from the bit as it gets less constrained. So those are general rules of thumb, but you really need to have the model tell you where the rotary speed sweet spot is.
How has the BHA designing evolved from earlier years till now?
Well, there are some vendors today that don't recognize these concepts, and they put a stabilizer on every tool. Reasons for that, you know, if if you have a big hole size, usually there's a fair amount of clearance between the tubulars, between the collars and the borehole wall. So you don't worry about the tools hitting the wall. But when you get to smaller hole sizes, the amount of clearance, like in this BHA, you can see there's not a lot of clearance between the collar and the wall. This happened to be a vertical hole section, but people will start to put in stabilizers because they want to prevent the tool from hitting the wall. Another way to address that problem is to put a wear sleeve on, which is the part of the BHA that will contact the wall and have hard facing on it so that it's not going to wear when it makes contact. And that can be an effective solution that some vendors have used when they don't want to put a stabilizer there, but they want to prevent the tool from wearing when it makes contact with the wall. And I've seen some of those be pretty effective designs when they use a wear sleeve.
Okay. So going into BHA design, like if I was to go to BHA design, what should I have to learn?
Well, there's a lot of art in API RP7G, recommended practice 7G, and API spec 7. Those are the documents that govern rotary, drilling equipment, the drill string, and they have things like bending strength ratios of connections and transition stiffnesses when you go from the big collars to the smaller collars to the heavyweight to the drill string. You want to make those changes in diameter and stiffness in a step-down fashion that's relatively smooth. So there's a lot of art about that API developed probably more than 30 years ago. And I think a lot of those guidelines are still pretty valid. And they help prevent things like washouts and, things that I guess on a component level, you can look at and say, okay, this is better design, but it's this theory about the stabilizer position is sort of a layer on top of that where you're looking at the dynamics of how all these things go together as a system.
So to finish it off, what would you say is the hardest step of your career?
The hardest step of my career.
Yeah.
Probably managing transitions between projects. You can, when you're in the middle of something, you've got a charter to go ahead and work on something, and there's a lot of support for doing something. When you go to work each day, what you need to do, and there may be, I have to figure X or Y out in order to move forward. But sometimes there's spaces where the charter to go ahead and do something has sort of come to its natural conclusion, and then something comes up, people get a lot of momentum and initiative around a new area, and you can go for several years working on that. So I think it's can be challenging going through transitions. Would be maybe one of the harder things.
Have you ever felt that you are not good enough, and how did you deal with that?
Well, I did have a person who asked me to give, this was a long time ago. He was actually kind of my mentor. He asked me to give, this is before the technology had developed to where it is today. I gave a lecture that he invited me to give, and then afterwards he referred to it as smoke and mirrors. So, there's always a lot of interpersonal dynamics, in work, and it's hard
Yeah.
But I think, everyone ends up making sort of alliances with certain people, and, you're closer working with some people than other people, and just have to sort of accept that there's going to be some interpersonal dynamics that happen at work.
Okay, let's not get to that. You've mentioned interpersonal dynamics at work. How do you deal with that?
Be patient. Avoid making things into a crisis. Just relax. Everyone needs to relax. Things will work out. Time is long. Just, chill.
Yeah. So do you have any parting short words?
Yeah. If you have a good idea, hold on to it. It may not be worked on right now. If an opportunity comes up later, and you see there's an opening for your new idea, right? Propose it again and see if you get to up. This industry has very long time scales, and I don't think many people appreciate it. And you look at computing technology today. It seems like everything happens so quickly. We're sort of on a different sort of metric. I know we have to, as an industry, work faster, but I think there's still elements of things because of the scale and risk that people will do things in a measured fashion. And we probably won't get away from that completely, although things are trying to move faster. But hold on to your good ideas. Maybe the time will come.
Yeah. Okay, thank you for your time and for this session.
Okay, well, thank you, Mercy, for inviting me. I appreciate it. It's been fun.